wrap up amortized complexity today by doing a couple of miscellaneous examples. So yesterday I was telling you about this move to front heuristic on linear list, and I said it is at most constant factor optimal to any scheme that does certain things, right? And it's interesting because something like that is open in the world of binary search trees, and that's known as the dynamic optimality conjecture. So let me state the claim and we will prove it using again a potential argument. So it's nice and simple. So what is the problem? We have a list of n elements. And we want to perform, let's make life simpler, and we're just doing access. So it's in some order, okay? So I want to access the ith element. Then what the algorithm is allowed to do is to it'll search for the ith element. Okay, I'll say access x, may not be ith element, whatever. So and assume x is in the list. It will go and search for x in a linear fashion, and then okay, it's allowed to move things in whatever way necessary the algorithm feels like at a cost. Okay, so what the algorithm will do is it will just search for and it will find x here, and maybe the algorithm, an algorithm that knows the future, knows what requests are going to come later, and so accordingly it may just go and after accessing x, it will do some transpositions, right? It will move things. It might move something and readjust it, and every so what is the cost? Okay, so access element x, right? And then the scheme of the algorithms we are going to look at is and then do transpositions. Any number of them, right? So this is the class of algorithms where we are going to work with and compare our heuristic with this class of algorithms. And what is the cost? Would be number of elements before x after the swaps, sorry, before the swaps, because if you moved x basically if x was somewhere here, this is the cost plus every transposition is also going to cost you something. Okay, and we will allow, if you want to move x to the front of the list, then that's we're going to give it a cost of free. So let's say it's free exchange if x is moved to the this is not important. You can even charge that length of that number of elements before x to the cost, but somehow it's simpler to argue this. So this is the class of algorithms. So you want a class of algorithms where it just goes and accesses element and in time proportional to where it's there, and then you are allowed to do whatever, and everything costs you something. unless you just want to move x to the front. That's like a free cost to you. Like I said, this is not even necessary. It's not that we are trying to define the cost to favor our move to here front heuristic or something. It is not necessary. So now the claim is MTF, the move to, so cost of MTF, what is this? So what I am going to do is that whenever I access x, I'll take x and move it to the front and nothing else, okay? And the total cost would be exactly number of elements before x, because this is free anyway. Now this we claim is at most 2 times cost of any other, or let's say opt. I mean, this opt strategy may actually know the future, and it might just say, oh, I'm not only going to move x, I will also know that maybe next 5 requests are going to be for these elements, I'm going to move them closer or something like that. So it might just do that. It knows the future. But of course, whenever it just does the transposition, there is a cost for it. And this is over a sequence of operations, right? For right, this is impressive because we don't know the opt strategy, and opt knows everything. It knows the future, and whereas this move to front doesn't know anything. It just does this, and so that's what makes this whole thing powerful. And the conjecture about splay trees is exactly somewhat similarly. We are as soon as we access the node, we keep moving, do these controlled rotations to move it to the root. The overall cost is, it's believed or it's conjectured, is some constant times overall cost of any other strategy which after accesses it just does some moves anywhere at a cost of you have to count the number of rotations as the cost. What we saw was that last time that actually splay achieves optimum cost with respect to static optimal whatever that cost is. But this is even more powerful, right? So in this case, the static optimal, remember we saw that if I know x1 is accessed with f1 frequency, x2 with f2 frequency, and so on, the static optimal thing would just do some pre-processing, arrange them in decreasing order of the frequencies. Okay, but this is saying even more. I mean, the static optima, we rearrange it and then that's it. You're not allowed to do anything. But here I'm just saying, no, after accessing, you're allowed to do some moves based on your knowledge of the future, for example. But even then, this heuristic. So is the setting and the cost and the model, everything clear? Okay, so now we are ready to show this. Right. So now the way we are going to do is that so we will show that the amortized cost of the ith operation is less than or equal to of my move to front is less than or equal to 2 times the actual cost of opt. And right. I don't know opt. I don't know what it's going to do, but somehow we are going to do some relation and prove this. So if you sum over this amortized cost, that gives you a bound for the actual total cost for move to front, and is at most 2 times the total actual cost of the opt. So we will show this only for this ith operation. Okay, right? We know that the sum of the amortized cost is equal to sum of the actual cost plus the potential difference, and so that gives you a bound for this sum gives you a bound for the actual cost, and this is the claim. Okay, so now let's how do I show it? I'm going to just define a potential and then plug it into the formula and things will follow. Okay, so this is due to, again, Slater and Tarjan, before they discovered this play tree thing. Okay, so what we're going to do, so here is my list before the ith operation. Then I do my ith operation and I get this, right? Whatever axis of move to front. And here I have the opt configuration. Let's call it this. I don't know this because I don't know what opt will do, but we'll. So my ith axis, let's say, is accessing this element, some element t here. So move to front will move t to the front and then move the rest as they were here. Okay, so let me define some sets here. Okay, so this has some set A and B. I'll define what is. So A is set of elements in Li minus 1 and in Li minus 1 star before T. Right, so A is also here. So T is here. So we will assume that the element you are looking for is always X. It's there. Otherwise, the cost is you go all the way and find out it's not there, and it's N. So you're not counting that. So A is the set of elements which are before T, the element you are accessing, in both the lists. B is elements before T in Li minus 1, but after T so there is B here. And you can guess the other two sets I'm going to do. After T in Li minus 1, but before T in Li minus 1 star. Okay, so this is C. And D is elements after T in Li minus 1 star and before no, in both after, sir. So now I'm going to define the potential. So let's make some. So what is the actual cost of move to front? Right. Yep. So move to front is not doing any transposition, it just moves T to the front. So that doesn't cost me anything. So it is A union B is cardinality, right? Cardinality of A plus cardinality of B. And okay. So now I'm going to define the potential, and what is the idea? The idea is that if this A union B is very large, if I am spending a lot of time, then somehow I want the potential to drop considerably, right. That is the whole idea of amortized complexity, right. So, the potential I am going to define of this list is the number of inversions between the move to front list and the opt list. So, between and the opt list. Okay, so L and A star. So, at any point of time, what is the potential is that opt is maintaining some ordering of the elements and I am maintaining some ordering of the elements, and what is an inversion is an XY pair where X appears before Y in one, but after if both lists are the same ordering, then the inversions is 0. Okay. So, how many pairs of elements which are appearing in different order between move to front list and the opt list, which I do not know, okay, but that is okay. This is all for analysis. Okay. So, now let us see, suppose, okay. Okay, so suppose opt, so this is what move to front will do. Suppose opt does not do anything, okay, after it accesses T, suppose it does not do anything, okay. Opt is you do not know opt strategy, it might not do anything, it might move T to the front or it might do some transpositions, any of this is possible. But for now, suppose opt does not do anything, then can you tell me the potential difference, right, if opt, or what I mean is if Li minus 1 star is equal to Li star, then the potential difference, let us say, then delta phi, what happens, right. So, now remember move to front has this picture because T has come here. So, now how many things are out of place and different in Li and Li star, or what is the change? So, look at the set A. Now, A was appearing before and after, so that is not a problem. Look at B, right. Elements in B appeared before T in Li minus 1, but appeared after T in Li minus 1 star. So, they contributed to this inversions, right, before. But now, after I moved it, everything in B also appears here and appears after T there. So, that would be a drop in the potential. The number of inversions would have come down by B. Agreed? See, the only thing you need to worry about is what the inversions are with respect to T, because the others do not change their relative position. So, whatever was there will remain now also and they will cancel out. The only thing you need to care about is with respect to T what happens. With respect to T, the set B was contributing to inversions before, but not anymore, because everything in B appears after T here as well as after T. So, it will be a minus B. What else? Plus A, right, because if you look at the set A, They were not contributing to inversions before because they were all appearing before t here and here. But now after you moved, the set A is appearing after t, but if you nothing op doesn't change, they are appearing before A, before t. So it will be plus A, and that's it, right? Because t moves here, so you only have to worry about t's inversions with respect to A and B. Everything else remains whatever it was before, right? Now, suppose opt does some inversions, transpositions, right? This is assuming if Li minus 1 star opt does not change anything. Suppose opt does some transpositions, right? Opt maybe moves things here, but every such move would contribute to at most one inversion. Because any transposition wherever will contribute to at most one inversion, an increase in at most one inversion. Because just you only suppose you swap some pair, then maybe that did anything with between any element, any of these pairs with respect to others, their relative positions don't change. So whatever the inversions created by them before or after, they are the same. But you only need to worry about these two guys. Maybe they were not contributing to inversion before, they will be contributing some inversions now. So suppose, so if Li minus 1s and Li stars are same, that means opt doesn't do any transposition, then the delta phi is this. And if opt performs some k transpositions, then delta phi is at most cardinality A minus cardinality B plus k. Each of them may contribute to at most one. In fact, the other case, if opt moves all the way t to here, it's a zero cost, and one can see that actually the potential is even going to come down, because even this A which was causing inversions are not even, the additional inversions are even not there. Okay. So my overall claim is that the potential difference after opt has done its transpositions, then between here and here, the potential difference is at most this. So we are ready to show this. So what is the amortized cost? Well, it's actual cost plus the potential difference. This is actual cost. And the potential difference, which is less A minus cardinality B plus K, because I said delta phi is this. Okay, thankfully the B cancels, and that is what is the actual cost of the optimum? Okay, we're done, because actual cost optimum takes, well, I don't know, but in optimum t is here, so it has to go and traverse through all of this. It's cardinality of A plus cardinality of C. And then it is doing some k transpositions. I have to charge for that. So it's clearly, I don't know, maybe C could be empty. So it's at least cardinality of A plus K. So this is at most 2 times that actual cost. That's all I wanted to show. Right? So from here we have the amortized cost will move to front is at most 2 times the actual cost of the optimum, because actual cost is at least cardinality of A. So somehow, I mean, the idea is that if you are spending, if t is so far away, the accessed element is so far away, then there's a huge drop in the potential, which means that is you are going closer to the opts thing that subsequently you and opt will more or less spend the same amount of time. Okay, that's the idea it's saying. Okay, so coming up with such a potential is a clever thing, and then you plug it in and it works fine. Okay, and I wanted to mention this because, as I said, something similar for split trees is the famous open conjecture. Okay, so this is one thing I wanted to discuss. Okay, and then next thing I wanted to do is some different forms of heaps, which are mergeable, and we get some amortized performance. Okay, so we saw that mergeable heaps. Okay, I'm switching gear here, and as I said, it's going to be a miscellaneous set of topics we'll do today. So did we see some variations of heaps where we can actually merge in logarithmic time? Fibonacci heaps, binomial heaps, right? We saw if you just take two binary heaps, they are not so easy to merge, even though it's nice to simple to implement in an array and so on. So we moved on to binomial heaps, which is based on binomial trees, huge collection of binomial Q, and then we said we can merge them in logarithmic time. I'm going to give you another heap where you can actually merge in logarithmic time and also do other operations in logarithmic time. And then we will see an amortized version of it. Okay, so that's the plan. So these are called leftist heaps. So it's a binary tree with values on the nodes satisfying your heap property. Okay, min heap, max heap, whatever the value at the parent less than value at its children, and so on. Right, but the structure of the shape of the tree is going to be where the difference is going to be. So let me define an external node. Okay, so what we'll do is we'll okay, so suppose I have a tree like this. So there is always value sitting on the nodes satisfying the heap property. Okay. I'm going to make it like anybody which doesn't have two children, I'm going to make it have two children by adding what are called external nodes. These are external nodes. And for any node, let me define dist is the length or number of edges in the shortest path from x to an external node. Okay, so for example, and distance to an external node is So this distance would be, for example, 1. This would be 2. This would be 1, 1. Okay, so here also would be 1 because I can just add this. Right, so these are the distance values on these nodes. Is it clear? So in general, distance at a node is equal to 1 plus minimum of distance of its left child So what is a leftist heap? You have or a leftist tree for any node x. So always the right path is the shortest path. Okay, so is this a leftist? What I have drawn, is it a leftist heap? So the leftist tree, and what is a leftist heap? Well, you know, structurally it is a leftist tree, and the values satisfy heap property. Okay. Okay, so is this a leftist tree? What I have drawn here? Looks like, because if you look at any node, the distance on the left is greater than or equal to the distance of the right. Right. So if I had this, then it is not a leftist tree, because here the distance is 1, whereas the distance here is 0. So, but if I swap it this way, then it becomes, okay, this is, yeah. Okay, so now I'm going to, okay, let's write some useful property of, so the height of the leftist heap can be large, but what? Something is small. Basically, distance at the root of a leftist heap. This is at most some log n. Why even have? Okay, we can prove this by induction, because anything to the right has smaller distance than the left. So how do you prove by induction? We've seen this kind of thing several times. So how would you show, whenever I want to show, how do you show height of a completely balanced tree is log n? Yeah, you just turn it around and say if the height is k, then it has at least 2 power k nodes, right? 2 power k plus 1 or something. Same thing we'll do, right? If you have the distance, okay, so I'm going to say because if I have a node, suppose its right distance is k, then if you look at the right distance here is greater than or equal to k minus 1, because it can't be less, because then the left is giving you k. And similarly, this right distance here is is actually equal to k minus 1. And then you apply induction here and you get at least 2 power k minus 1 nodes and so on. Also, once you have a tree which, it's easy to make it satisfy this condition, because, for any node, you just look at the left and right, and if the right is larger, you just swap the subtrees, right? Then the left will become larger. You don't have to do anything else. The heap property is satisfied, everything else is satisfied. So you can just go top down, and whenever you have a tree where it is not satisfied, you just have to swap the tree children, right? If for any node violated, then you just swap them and you're fine. So now we are all set. Suppose I want to merge two leftist heaps. How do we do it? And I want to do it in logarithmic time, right? So leftist heaps, suppose n1, let's say that had n1 nodes, and h2 that had n2 nodes. If I want to do logarithmic time, all I have to do is to look at their rightmost paths. And I know that they are of length at most log n1, log n2. Merge both of them, and you get one long path. Stick the remaining subtrees as they belong to, and then fix to ensure that the whole thing is a leftist heap, right? So I have some right path. Maybe this is something here. Maybe this is nothing else. No, I can't do it because something like this. So let's say A, B, C, D, and then I have the other heap where I have some. So first thing I'll do is I'll do my standard merge, as I will do in merge sort or something. Merge these two lists. This is of length log n1, this is of length log n2, so I can merge them in logarithmic time and get one long path, and stick these subtrees exactly, as, so if this node has landed up here, then put this subtree as a child of here, and so on. So all these subtrees just go and get there, and you spent only logarithmic time. Now you have to make sure that this property is satisfied, right? And the only path you need to verify is this new path you created, because everybody else, all these trees were leftist trees to start with, so you didn't have to do anything about swapping them. So you just run through the path, and for every node, you need to update the distance value, so that you have to do it cleverly. So if we'll store that this distance information at every node. And you should be able to update them in this logarithmic time, and whenever left right violation happens, swap them. Okay, so I'm not going to get into the details, but it's fairly simple. Right, so maybe I'll write down at least. Now think about how would I implement insert and delete min, right? These are the other two operations I care about in priority queue. So the algorithm is merge the two rightmost paths based on their values. Update the dist values. Traverse the new path. And ensure distance on the left is greater than or equal to distance on the right for every node. By swapping the left-right subtrees if necessary. So this whole thing. Okay, so it turns out you can use just merge to implement the other operations as well. How do you insert? You create a new leftist heap with one node and merge it with this. Okay. How do you do delete min? Delete. You have two subtrees, merge them. And both are leftist trees, leftist heaps. So right, so the corollary is that you can do insert, delete min, merge all in. Okay, good. So this is just, I thought, another variation of heap. There are quite a few variations, and this is simple enough. I mean, the good thing about Fibonacci heaps is that they have constant amortized time for this decrease key operation. I don't know how you would do decrease key operation here, or an arbitrary delete element. And yeah, I guess even arbitrary delete should be possible because you have these two subtrees, merge them and replace this entire subtree by that node. Okay. But constant amortized time, I'm not sure. But this is all worst case, right? We have now what I'm going to tell you is another variation where you have a logarithmic amortized time. Surprisingly, it's a lot simpler, and we don't maintain anything about this distance information or anything. No condition. Yeah, it's like splaying, right? After we'll essentially merge the two right paths and then do some swaps, and then we'll argue that everything works out in the amortized case. Okay, this is so leftist heaps. No, this is not due to Tarjan, but what I'm going to talk about is Skew heaps. I think this is maybe Slater is also involved. I don't know. So we maintain nothing. You have a binary tree with heap order on the values. That's all. And the way we actually will do the merge is where all the fun is, right? It's like splay trees. It was a binary search tree, and we didn't do anything, didn't maintain anything. But whenever you were accessing, we were doing something, and that's what makes it sort of self-adjusting. And this is, you can think of it as a self-adjusting heap. So what we'll do, so you have you just have values satisfy heap order. So the parent is less than evaluate its children, and that's all. And how am I going to do merge? I mean, the inspiration I think is from the leftist heap, but this is going to be sort of self-adjusting. So merge the rightmost paths of H1, H2. You have these two heaps which you want to merge. Now, if I just leave it here, I have a problem because the rightmost paths are going to become bigger and bigger, causing me a high cost in future. So what we'll do is, okay, so, and then of course we're going to place the other subtrees wherever they belong to, and then we're going to say, just simply swap the left and right subtrees of every node in the path. Except the bottommost. I don't know why, but let me see. That's all. So what we'll do, we'll so you have this, and then here is another. You're going to merge these two, and you get one big path. And so I'm going to stick the rest of the trees. Then I'm going to go through this path and then swap the left and right subtrees for every node. That's it. Okay, and somehow we're going to argue that things all work out in the amortized sense. So the trick again is to come up with some potential function. Yeah, so let's a non-root node X is called heavy if, I already defined the size of X, right? Yesterday when we talked about splay, the number of nodes in the subtree rooted at X, including X, is greater than or equal to half of S of parent of X. So what is S of X? Number of nodes so when we say the subtree, that is including X. Okay, and it's called light otherwise. Actually, I think I want to say strictly more than half. Probably doesn't matter. Okay, so is the definition clear? You have this tree, and if one child carries more than half the number of nodes of the total subtree of the parent, then I'm going to call it heavy, and otherwise it's light. Okay, so here is a little observation. See if it's easy. What can you say about number of light nodes in a root to leaf path, right, in a tree on n nodes? Any thoughts? Log n, okay. Why? Right, right. So if I am light means that, so let's look at this. Suppose this is light means what? That the number of nodes in the subtree is at most half of the number of nodes in this subtree, right? And then let's say there is another light node in this path. That means the number of nodes in this subtree is at most half of 1/4 of the number of nodes in this subtree. Okay, and so on and so forth. So you will not have more than log n many light nodes in a path, because whenever I have a light node, the number of nodes decreases by a factor of 2. Okay, that's all. Yeah, so now let's see. So suppose, so what I have to come up with a potential, and it's going to be based on all this light heavy kind of nodes. So if I spend, if I spend some h1 plus h2 time for my merge here, I want to sort of kill this cost using potential, right? So no, I don't want to say, okay. Yeah. Okay, so the potential, let me just say it. I've been sort of trying to give some intuition. Number of heavy nodes that are right children. That's my potential. Okay. So in my tree, I look at, so the heavy nodes are the ones which are causing problem, because that can be large, because I know in any path the number of light nodes is small within my bound I want logarithmic. So it's just the number of heavy nodes which can be. So if I look at this, when I am trying to merge this two right paths, suppose h1 is the number of heavy nodes here, and h2 is the number of heavy nodes here in that path. Okay. Of course, there are more nodes here in that path, but that number is not more than log n1, log n2, because the light nodes, this observation says, So the actual cost is h1 plus h2 plus some logarithmic cost, and I want h1, h2 to be killed, right? And But now by doing this swapping, I am going to move them to the left. Whatever which are heavy, they are not going to be right heavy, right? These are not I am not just counting number of heavy nodes that are right child. So by doing the swaps, these guys which are heavy on the right are going to become left children. So that I am going to kill that H1, H2 by using my potential. But then I am going to have some new heavy nodes that might show up, and I have to bound that by some logarithmic, then I will be done. Okay. So let me say what, so the amortized cost for my merge operation equal to H1 plus H2 plus, or at most, log N1 plus log N2 plus so what is this? This is potential after, this is potential before, and H1 is number of heavy nodes in the rightmost path of the first heap, and H2 is in the second heap. Right. So this constitute my actual cost, because actual cost is the merge cost, or whatever proportional to the length of the path, which is H1 plus number of light nodes, which is at most log N1, H2 plus number of light nodes here, which is at most log N2. So that sum plus the potential difference, right. So the potential, I mean, as you can see that H1 and H2 vanish, because they are no longer, these nodes have become left, they have been swapped, because I am doing swap the left and right subtree. So these guys, so if I have a node which was a right heavy node, then since I have done the swap, it would have become a left heavy, not right heavy. But I might have created some new right heavy nodes, and I want to bound it by some logarithmic in N1, and then I am done, right. So the potential difference so observation That's it. That's all I need. Finally, I need to use that to do that. Okay. So first of all, the H1, H2 trees have been swapped, have become left subtrees. So that's one. So that is a potential drop, okay, to nullify this H1, H2. But we might have created new heavy trees. Yeah. So where are they, right? Clearly, if you look at any of these nodes, these subtrees, they remain intact. As subtrees, we have not changed them. So if if whatever right heavy or left heavy nodes there, they will be cancelling each other. So the real problem is only the subtrees of this merged node, okay, which now has actually become a leftmost path by your swapping. So these right. So these nodes, no, so it's only the sum of these guys. Yeah, if this was probably, yeah. So I had a node here which was light before, okay, but light because yes, this was light, but now I have moved this here and moved here. So this guy which is heavy has become a right child, and so it's going to contribute to my right heavy node. Okay. Sorry. So let me just go back. No, I said, oh, all these guys are intact and all that is not correct, because it's not just, we are not counting just the heavy nodes, we are counting those heavy nodes which are right subtrees, right. So within them, if somebody was a right subtree, they remain as a right subtree, right heavy, they cancel out. But these subtrees themselves, some of them could be heavy, but we did not count them before because they were left subtree, but now they have moved to the right subtree and we are going to count them, okay. But then first of all, they are all subtrees of this path, number one. Number two, if this was heavy, that means that this guy, if this was heavy, its sibling would have been light, right, because if one weight was greater than, strictly more than, then this would have been strictly less than. So sibling would have been light. So but I know, so for all the new heavy nodes I have created, their siblings were light in that path, but the number of light nodes in that path is at most log. So number of, okay, so let me just add new, but they are all subtrees of this output path. And B, their siblings in the path, the siblings are in the path, are light, hence there are at most log n or log n1 plus n2. No, log n of them, because we know that number of light nodes. Okay, log n1 plus n2. So my potential drop would be, okay, so this is what I wanted to say. It's at most some H3, the new right heavy nodes, minus H1 minus H2. But what I have argued here in my B is that this H3 is at most log n. Now you plug it in here, H1 H2 cancels, and so you have another log n, so it will be at most. So here is a log n, maybe about 3 log n. Okay, so if you look at it as a what we maintain, nothing except heap order. Just when we are doing merge, we just merge the rightmost paths and do the swaps, the left and right subtree. Essentially, if you're spending long time because the right subtree lengths are large, the potential drops, that you can use the potential in the data structure. And yeah, and if you can do merge, you can also do inserts and deletes, exactly, delete mins, exactly like what we did before. But inserting is creating a new heap and merging with it, and delete min is delete min and merge the two subtrees. Yeah, but of course, this is amortized cost. For the leftist heap, the bound we saw was worst case, but here it's the amortized cost, because you do have these paths sometimes very large. Okay, I think I will stop, and that's more or less quite a lot on amortized complexity, but it will come with us because it's not just, it's just a paradigm, right? So when we look at some other algorithms, for example, in string matching or something, we will see that visualizing it as the amortized cost will help us get the ease the analysis. So, but it's just another way of useful cost measure of analyzing data structures particularly, but sometimes also in algorithms.